Water in Space is the title for my presentation, because we are basically covering the hydroplanet model from the universal model of science. The universal model, a new millennial science, is a really unique book, the largest collection of new scientific discovery that's ever been published. So the hydroplanet model, my name is Alan Wade, and this is volume 1, and there's about 800 pages. There's 4 introductory chapters and 5 science chapters. We're covering just the first part of the hydroplanet model today. And then later on, I'm going to be doing an introduction that will take little pieces of 4 of these chapters, 4 of the science chapters. So, and some of my presentations that are already posted on YouTube that we've done in previous months talked about magma and how it didn't really work. And here's some quotes on that. The nature and timing or even existence of magma oceans is uncertain. Okay. So we know there's lava, and that was one of the questions we had to wrestle with is magma the same as lava? Because we think of them the same, but magma really is talking about the whole center of the earth being filled with this molten lava, okay? And in the presentation before, I kind of explained that it's really a surface phenomenon that happens in the crust. So the history of how Earth's interior evolved and how it accounts for many aspects of the planet's behavior remains largely unwritten. Taking water into account could well help explain a great deal more. Well, if it could explain more, then we need to explore that, and that's what this chapter is all about, is looking at water and how maybe there's water inside the center of the earth instead of magma. So, from seismic observation, geologists know that the Earth's crust is a lithosphere and is floating on a liquid. The fundamental question is, without magma, what other liquid could the crust be floating on? So, if you want to go ahead and answer that question, what other liquids do you know of that the crust of the Earth might be floating on?
Jello.
Jello.
Water.
Water? All right. Okay, we've got 2 suggestions here, Jello and water. All right, and of course magma is the standard theory that's taught to elementary kids in 3rd grade all over the nation. So we've got some different ideas, and we ought to explore and look at those. The universal model is going to lean towards the water, and we're going to start in this presentation. I titled it Water in Space, because as we look out into outer space, we see water everywhere we look. And one of the questions we're going to start with is, why are planets spheres, like round balls? And we're suggesting that it's because they form from a liquid. So without magma, what is the only other liquid in space? And water is the most prominent liquid in space. And in space, liquid water will form into a sphere. These little pictures down here are showing the astronauts out in the Universal Space Station and stuff, doing experiments and stuff with water. And it always collects into a ball because of the surface tension of water. It will ball up and it sticks together. And so sometimes we think of like rain as teardrop shapes, but really, if it's not moving, or like here in this case it's pulling apart, it's not in that shape. It actually goes to a round shape once it's released, or you don't have the friction of going through the atmosphere when it's raining. So in microgravity, water droplets form free floating spheres, as you can see up here. And again, that's another astronaut. And you can see, it reverses the image, so it's upside down. And again, more astronauts looking at balls of water. And you can look it up on the internet and find lots of pictures and experiments like this, even videos showing them playing with the water in space. So how does liquid water exist in the icy cold depths of space? Perhaps the most exciting property of interstellar amorphous ice is that when it's exposed to radiation, such as that found in deep space, it can float, even though its temperature is a scant few degrees above absolute zero. The discovery that amorphous ice is more like liquid water than it is like crystalline ice came as a huge surprise to the scientists, but that's what they're finding. So how much water is there in outer space? So it must be raining in Orion. It has a very strong water line, so this is showing through spectroscopy and this spike is right where the identifies water as the element that they're tracing. And so as they're looking out at the Orion Nebula, that's what they're seeing. And it's 20 times stronger than the previous one, which is much more than they would have expected. When researchers found even more water, there were a number of other sources as well. And the nebula W49, a cloudy region in which new stars were forming, had water radiation 20 times as bright as that of Orion. So the spike on it would be 20 times more. So and that's where new stars are forming. So water is very important even in the formation of stars. The water molecule plays a fundamental role during the first stages of star formation. That's a quote from Science. No space masers have been found more powerful than those based on water molecules. And what substance is the most abundant in space? Based on the power of its cosmic radiation, which is what they're measuring on that spike on Orion, and the answer is water, because we're finding it nearly everywhere that we're going and looking and measuring that. Okay, and Saturn's rings are primarily from water ice. Okay, pretty, and reflecting some sun. Here's some other quotes for all the planets. So is water found in other planets? Indeed, Mercury, the closest planet to the sun, poses a lot of ice, 100 billion to 1 trillion tons of ice, and yet that's the closest to the sun. Venus, there was once 100 times or so more water, enough to make a wading pool over the surface, if not a whole ocean. Jupiter, from the spectra we obtained, water vapor relative humidity between 4 and 8 bar. So again, that spectra is that spike that we saw in Orion. So that's what the scientists are actually measuring. Uranus, far below the visible clouds, are probably thicker cloud layers made up of liquid water, maybe an ocean of liquid water. And then Neptune, scientists believe that Neptune is made up chiefly of hydrogen, helium, water, and silicates. So, the most important discovery in space exploration in the last 25 years was the confirmation of large quantities of water ice on Mars. And I don't know if you heard the new news recently from NASA. They're actually saying that there's an underground ocean that they've recently detected on Mars. So that's some new news that came out. I actually posted a link on my Facebook page, Do True Science. So if you wanted to read more about that, you can check it out there. All right. So big news. Okay, exoplanet water. On the 24th of September 2014, researchers found planet 4 times the diameter of Earth, orbiting a star in the Cygnus constellation, 124 light years away, with significant quantities of water vapor. So even in those other solar systems, other areas, they're finding planets with water. Okay. And so another thing we want to look at is our own moon, because the universal model claims that it's a hydromoon. So that there's a lot of water inside that. Even though the water has evaporated off the surface of the moon, so it's pretty dry on the outside, it we believe formed from water. And a lot of the craters come from water when it was more liquid. Okay. Comets, the rate they shed gas as they approach the sun, says that water ice is the most abundant substance in nearly all of them. Okay? In fact, the tail of comets is from water escaping from. I know I didn't know that for a long time, but maybe you already do. But yeah, so it's the sun reflecting off the water vapors that's getting sprayed out from the comets. That's what their tail's from. And I saw one report saying it's like 80% water. So, okay, and water above the Earth, the SOHO satellite, they big telescope camera they put up in space, and at first it wasn't working, and it was because ice had collected on it. So water vapor had got on and frozen on the lens of the camera, and so it was a big problem. Fortunately, as it's moving around in space, at one point it turned towards the sun, and the sun melted and the ice and then worked again. But, you know, they thought it was a, millions of dollar problem that it wasn't working at first. So why are larger bodies spherical, whereas smaller bodies have the irregular shape? And, like you hear about asteroids, right? And usually when we think of an asteroid, we think of something that's very like a broken piece of rock with really sharp, jagged edges. But if you'll notice these that we have pictures of, even those, they're not round and spherical, but they're still relatively smooth, with little pits from and little craters in them. Okay. What is a hydrosphere? So hydrosphere.
Water circle?
Yeah, water circle, there you go. Okay, or water ball, all right. So that's kind of what we're saying these planets are, a spherically shaped celestial body with large amounts of water and ice. And the scientists are actually finding these all over the place. In fact, I've got a segment in later where I'll show you some of the pictures from NASA and stuff. They're calling them water worlds. But anyway, hydrosphere is the word we're using in the universal model. So, Tethys hydrosphere is a moon known to have density very close to that of water, indicating that it's likely composed mainly of water ice. And so it's one of the moons of Saturn. You can see the Saturn's rings here in this picture with it right above them. Okay. Let's see. Somebody else want to read one of the quotes here?
I
Okay, go ahead.
The composition of Titan's solid ground has thrown up a shock. It's made of water ice rather than rock. It rhymes.
Yeah, that's right. Good. Okay, and this is showing you the size of the Titan Lake there compared to Lake Superior. So it's a big lake there on the surface of Titan's, which is, again, one of the moons in our solar system. And these are actually this montage shows 4 of the major icy moons of Saturn. All of these bodies are made largely of ice. So, and I'll have more pictures of enceladus later. The big one here in the middle, but Rhea and Hephaestus and Elon are all water worlds, as NASA's calling them. Okay. So the crystallization process. So I think we've established, right, from all these images that there's a lot of water out in the solar system, and even beyond our solar system. And we're suggesting that the reason that these planets and moons are round is because they originally formed from a ball of water, and then the rocks, like on the surface of our Earth, crystallized out of that water, and then were spun to the outside. So, so we think that that's why a lot of these planets are round. Okay. Are there any questions about that before we go on to the crystallization process? Okay. Good. All right. So we're saying that they form in round balls because it starts out as a big ball of water in space. All the elements, if you're collecting elements from space, water's very abundant, and it's found everywhere, and we can collect it, and when it collects and condenses into one mass, not solid, but one mass, it forms into a round sphere, and if there's other elements in that water, then crystals can form. And so that's why I wanted to make sure that's clear before I go into the next thing, because the crystallization process is now chapter 7.4, and it is going to explain that all natural crystalline minerals formed in water. So we can have the minerals that form the crust of the Earth forming in that deep water. If you've got a ball of water the size of the Earth, right? That's some deep water, and and plenty of minerals maybe mixed in with that water so that the crystals can start forming and growing. Okay, and these are actually some fluorite crystals, and they have some of those. So I'll pass these around so you can kind of look at some of them. You can see a little bit different colors, some greens and some purples and some more clear ones. But they all have a very definite shape, a definite structure. These fluorite crystals form with, 8 sides to them. And so 4 on the top, 4 on the bottom kind of thing. And so they're kind of pointed almost like a diamond shape, but as we talk about this, we'll see all crystals form in water. So like sugar crystals, these are crystals that formed on a string suspended in saturated sugar water. So, and have any of you done that experiment before? Okay, you have. Good. All right. From the Journal of Marine and Petroleum Geology, masses of solid salt may form and accumulate underground independently of solar evaporation of seawater. So they're realizing because some of these salt deposits are so vast and so deep, they couldn't have just formed from surface evaporation. Because that's obviously one of the theory for how salt deposits form is just through, salt water, like from the ocean, evaporating. So they say that shallow seas covered the ground and then evaporated, but that would form a very thin layer of salt, and we've got salt deposits that are miles deep or thick, and so it couldn't quite happen that way. Do you want to read this one?
Sure.
Okay.
The Norwegian research team demonstrated how solid salt forms in high temperature, high pressure conditions when seawater circulates in hydrothermal systems in the crust or under the piles of sediment.
Okay. So maybe under piles of sediment, right? So this is not surface evaporation, but high temperature and high pressure. Those are important keys, and we'll see that more as we continue to talk about it. So geologists whose current model of salt deposit and accumulation relies only on solar evaporation from the sun of seawater have overlooked this novel hydrothermal outsalting mechanism. So, and this is showing the salt dome. You can see a salt plug that may be miles thick. And it's interesting that in addition to the normal sodium chloride, like table salt, that may be thick and solid. Let me go ahead and pass around. All right, so this is a piece of salt, sodium chloride, and you can see if it was from evaporation, there would be lots of layers, and during that evaporation process, right, you'd have some wind and dust coming in, so you'd end up with lots of layers, but you can see this is pretty much just solid salt, and like in the salt plug on this picture, it could be miles deep, okay? And it's interesting, they tend to find petroleum deposits right near it, and on the top, they have these other forms of salt, the anhydrite and the gypsum and the limestone are other deposits that they find, like in the limestone there's sulfur, but let me go ahead and pass around some gypsum salt too. This is, these are actually selenite, but another form of salt that, so the anhydrite and gypsum there are always related to the salt, slightly different forms that tend to cap off this salt plug. So we really need a better explanation for how salt forms. Okay, and then in hydros, and if you haven't heard of an anhydro, then you do need to find out more about that. Let's see. Let me go ahead and pass this one around first. This is a
You need my flashlight?
amethyst crystal. Yeah, that would probably be good. I actually have a couple in my bag too. So this amethyst crystal actually has a little water pocket with an air bubble in right there. Do you see that moving in there? Okay. And, okay, so you can see that. Okay, so right over on this side, there's a little air bubble in a water pocket. Okay. Do you see it there moving? Okay, you do? Okay. Yeah, so. This is another kind of. So yeah, why don't you get your flashlight and go ahead and show that crystal to everyone else, and show it with the light. Okay, so this is a different form. You can see these are quartz crystals. These four on the outside are quartz crystals that have anhydrous in. So it's pointing to the little bubble there, just like you could see in the amethyst crystal that I showed you. These are a little different style, more like the one at the top, kind of like a geode, and they realized that there's water inside, so they polished the outside instead of cutting it open to show the inside. So if you'll hold this kind of firmly on the edges and then kind of shake it by your ear, you'll probably feel it more than you hear it. But go ahead and try that. So I've got 2 of these you can try and pass around. So, okay, so essentially it's kind of like a geode, right? But there's water on the inside, so they polish the outside. Or in this case, they were able to slice it so you can see. So it still has it's unpolished on part of the outside, but they cut it flat on one side so that keeping the chamber intact. All right. So those are anhydrous, and it's surprising that there are different varieties and kinds, and you can see those. But they have water trapped inside. Now, one of the factors of this is if the planet was a big ball of magma, like those who believe there's magma inside the center of the Earth, they believe that the whole Earth was a big, huge ball of magma at one time. And yet, that wouldn't make sense if there's water trapped in crystals, right? It wouldn't. That wouldn't work, right? Because if these get too hot, in fact, I was kind of worried about it today in the Arizona heat. And so one of the first things when I got in is I checked that and made sure that it hadn't cracked open, because I have heard some of my friends have had anhydrous like this where they crack and all the water leaks out because they got too hot. Or that it evaporates over time. And then another thing is, if there was an ice age, it's kind of hard to get a rock like that in an ice age too, because it could freeze the water inside and then crack it open too, because water expands as it freezes. So it kind of throws off, those anhydrous kind of throw off those theories. So hydrofountains is another important thing that it talks about in the universal model. And we see them on Enceladus, that moon of Saturn. But we also see them on the Earth. There's hydrofountains erupting every day around the world as geysers. Yellowstone, they can, time them on the clock. They know, like Old Faithful is really regular. And they're erupting every day, and every, I think, hour and a half at Old Faithful. What would you say if somebody told you that all natural rocks contain water, right? I mean, these anhydrous have a big, a bunch of water in a section, but did you realize that all rocks have water in them? Ever thought of that? Not really, right? And one of the ways that they do this experiment, we actually did a similar experiment when I was in college, where we took carrots and cut them up and then cut them in thin slices and then put them in an oven to try to determine how much water was in the carrots. It was about 80% water. But you can do a similar thing with rocks, crush up the rocks, put them in an oven, evaporate the water out, and then weigh it again to see how much water was lost, how much of the mass is less after you crush it and cook it in an oven. And most natural rocks will have water in them. Some I've heard as high as like 30%. But, so it's surprising how much mass may come from the water. So the density of Jasper is 2.68 grams per cubic centimeter. And the weight loss after vacuum heating at 800 degrees for 12 hours is 0.5% the weight percent. So, so it's half of a percentage, but that's still, you know, surprising amount of water in Jasper, which is a pretty solid rock. The density of flint, 2.59 grams per cubic centimeter, and the weight loss after vacuum heating at 800 degrees for 12 hours is 1.5% weight percentage. So that one's quite a bit more. Of course, a lighter material. It's not as hardly crystallized. So, with those things that I've said, hopefully I've showed you that crystals form in water, and that's a pretty well accepted scientific fact. And the universal model has actually done experiments where they've made crystals, and so we know the environment, the recipe for forming crystals. These are some that were made at a lab, and this one actually does have a little anhydro in it. If you tip it side to side, you'll see a little water bubble there moving back and forth. I think it moves pretty slowly because it's a pretty small little crevice that that's in. And you can see some of these are pretty ornate and pretty. Delicate quartz crystals. And I asked them how these form, and they're forming with more than 10,000 pounds per square inch of pressure. So it's an awful lot of pressure. And and this is another man-made crystal. In fact, you'll notice there's a little wire sticking out of one side, and if you look at it from the side, you'll see there's a clear section, and then the green crystal is growing off of either side of that what they call a seed crystal. So they start with a little piece of quartz crystal as a seed crystal. When they use this wire to lower it into the water solution, it's a silica rich, so it has high minerals, but they're growing this then in a short period of time with hot water and this silica-rich mineral water, and with pressure that is equal to 10,000 to 14,000 pounds per square inch. Now, you guys have probably swam in a swimming pool and gone down to the deep end and felt some pressure in your ears, right? Well, how deep do you think the swimming pool has to be to get 10,000 pounds per square inch? Pretty deep, yeah. We've calculated it out. In fact, you can look it up and calculate it out. About 5.5 miles deep to get that much pressure. And that's the kind of pressure you need to form quartz or amethyst crystals like this. So there must have been a time where there was 5 miles of water. Like, I took a trip last month. I took a group of students up to the petrified forest. And those are basically quartz-based rocks that have crystallized. These are a bunch of petrified wood pieces. And if you look at them, you know, I got information up there. You can see some of the bark on some of them, and you can see some different colors. So the white is more like a standard quartz-based rock. I'll let you pass that around if you want to pick up another piece and look at it too. In fact, you could take a home sample if you want of that petrified wood. But like I bought a postcard while I was up there that showed the different minerals that are giving it the different coloration, but it's basically the wood has turned to quartz-based stone. And the only way that can happen is under 5 miles of water. It doesn't just happen by chance. and so there must have been a time where there was 5 miles of water above the surface of the Arizona forest before it became a desert, and you know, the painted desert, to turn the forest to the petrified forest. And so that's all part of this crystallization process. And volcanic rocks look like this. They're lightweight because the holes that are caused by escaping steam. And I'll go ahead and pass around some samples of that as well. Here's a couple examples of that. You can feel that they're very lightweight. And you can kind of think of it like pancakes, right? The bubbles come out of the pancakes, which is water turning to steam and creating this bubble or air pocket. And some of these pieces of volcanic rock like this will float in water because they have so many air pockets in them now. Since the water's escaped, they're now lighter than water.
How Hawaii floats?
Yeah, no, is that how Hawaii floats? Good question. I don't think it's exactly that, but that's fun.
But what about the volcano that's going off over there?
Yeah, it's forming a
So-
new island.
So it's forming another island. One of the things that I found interesting on the news reports is that before that volcano started erupting, there was a report of an earthquake. And so, as we'll be talking about later here, there's the lava is caused by frictional heating from the earthquake. And so that's how how lava is formed.
You want me to read that one?
Yes, please.
Okay. No consistent identifying features are known at the present for the reliable differentiation of synthetic from natural quartz, and the two types are so far indistinguishable.
Right. So, I mean, could you look at the synthetic man-made crystals and distinguish anything different from the natural crystals that I showed you too, right? They look very much the same. Okay, and so here's synthetic quartz crystals grown in the former Soviet Union. Again, you would think that those are natural crystals if I just showed you a picture. You know, and the one, fortunately, they left the wire in it, so we know that's a man-made crystal. Okay, calcite crystals. This is a specimen of calcite, the second most common mineral type on the continents, next to quartz-based minerals. Large calcite crystals, such as this, have only been found to form in a hypertherm. So we haven't actually come up with that definition yet. Sometimes we mention it in our introduction. But hypertherm, if you cut it into three pieces there, hydro is for water, and then pre is for pressure, and therm is for the thermal heat. So you need all three of those, because everyone's heard of a hydrothermal, but that's just water that's hot, and you need that 10,000 or more pounds per square inch of pressure in order to form crystals. So that we define that new word. So since the old geology does not work, this is a messed up picture of the whole magma rock cycle pseudo-theory, and we actually talked about that rock cycle and how it doesn't work last month in our meetings. And so we actually need a new geology now that takes into consideration this pressure that's required to form rocks. And now, since we've made man-made quartz crystals, we know the environment that rocks have to form in, and so we need to take that into consideration rather than thinking everything came from magma. Okay. Any questions about that? Maybe I should put that out there in case anyone had a question on that. Because now we're going to kind of transition to a different thing, starting to talk about Enceladus, the hydro fountain. So hydro fountain, we kind of mentioned when I talked about geysers earlier. A hydro fountain is like a geyser, so water fountain, hydro fountain, is like a geyser. Usually it's caused from heat that will heat up the water enough that it also is forming some steam, just like in the geysers in Yellowstone. That steam then pushes the water out, right? Because when steam expands, the volume will change 1,700 times the volume. So if you have a little bit of water, it'll expand to about this much volume of steam. And so if that's happening fast, like would happen when you have rocks heating up enough that they melt, the water inside the earth just explodes. And kind of like Mount St. Helens, right? The whole mountain got blown off because they were measuring the earthquake activity, and then if that water turned into steam, just explodes it. So, but this is, again, Enceladus is, this is a picture of Enceladus. It's one of the moons of Saturn. So that's why they're showing it with Saturn. And that is a picture that we have of a hydro fountain exploding from Enceladus. And if you look at that, the amount of water getting sprayed out of the side of that, I mean, it's almost as big as the planet itself, right? That is huge, okay? So if you can imagine that, and one of the reasons is because the gravitational pull of Saturn, because it's close, and some of the other moons around Enceladus create a lot of pull and gravitational forces that cause these fracture lines, like earthquakes, all over the surface that allow the water to just spray out of these cracks. And again, the volume is hard to fathom, for us to fathom, because we've never seen geysers that big, right? Old Faithful goes pretty high, but that one's almost the size of the moon itself. Okay, so hopefully you kind of get in the picture here that the Earth doesn't have magma all the way in the center. The liquid that's in the center is actually water, and there's a solid ice core with water around that, and then the rocks and water all mixed in the mantle that's around that. And then, of course, the solid rock crust is only like, if we took the Earth and shrunk it down to the size of a basketball, it would only be as thick as a sheet of paper. So that rocky crust that the continents are is very thin in comparison to the rest of the whole Earth. And we know that there's the liquid inside because the seismic waves we can measure, and we can see seismic waves don't go through liquid like they would through a solid. So we know that there's liquid in the center, and scientists have said, well, that's where the magma is. But we're saying that that's just water. But it's so deep we haven't, we can't measure it. Nobody's seen it. So to talk more about NASA and the water worlds that they're coming up with, I collected some pictures from the internet. These are pictures from NASA. Again, they're seeing water everywhere they look in the universe, even on the sun. And this is what they're expecting through this spectroscopy. They're expecting to find from, I'm pretty sure that's Enceladus. Does it say? Doesn't say. But here's water just off the charts compared to other things. But they're also finding some carbon elements like methane, which is CH4, and ethane, C2H6, and carbon dioxide is over here, carboxyl sulfide, carbon monoxide. Those are some of the high ones, and they've got other lower ones as well that they're measuring. And because they're finding some of these with carbon in, that's why they're thinking, well, maybe there's some life out there too. This is another image kind of showing what they think the crust of Enceladus has a large ice sheet and then has this water underneath it. And because the Cassini spacecraft circled and went right by this and found the sprays of the water from there. So this is big news. Again, this is a picture of Enceladus, and you can see the cracks and fractures in that ice crust. And I think, and this is one actually showing the rest of the picture, because the other one before was just this part zoomed in. But this is how they think it really is. That they think there's a rocky core underneath, but you can see this is 5 kilometers, and they're saying that the water underneath that is 65 kilometers. So lots and lots and lots of water. And then they're saying that down in the bottom, where the rocky core has a crust, that there are these hydrothermal vents, like we're finding on the bottom of the ocean here on our Earth. And these hydrothermal vents create enough heat to that maybe there's, like, we're finding new life forms down in the bottoms of the oceans where we didn't think anything could live. We're finding new life forms down in the bottoms of the oceans around these hydrothermal vents. And so they're thinking, well, maybe there's something down there that may be living. But anyway, definitely some very interesting geology and hydrology when you think about 65 kilometers of water. Any questions on that? Okay. All right. And this then is another moon of Jupiter. So we've got Jupiter in the background, and they're again showing this icy crust with a thick surface of water that goes much deeper. There it is there. So this is that moon. I'm trying to think. It starts with another E. The name of it is slipping my mind. I didn't get the name written in there. Sorry. It starts with an E. But anyway, it's a moon of Jupiter. That's a lot. Okay, so that's it on the water worlds and hydroplanet model.